Okay, this is the video for the complete U substitution technique. Basically the second half of these yellow notes. This is the lesson three. It's the second half of lesson three. Excuse me. So the situation here is that sometimes our substitution doesn't fully replace the old variable, usually the x that we're trying to replace, which isn't, convenient, but we can fix it by using two versions of our substitution equation at the same time, one of which is solved for u. That's what we've typically been using thus far, but we'll come up with another version that is solved for x. Let's see if I can zoom in a little bit on example 8. Give me just a moment here. That might be the best it's going to let me do. All right, so in example 8, we've got this integrand here. We've seen in the past that the stuff inside a radical is usually a good choice for you. Unfortunately here, we've got this extra x squared, which isn't the derivative of 3x minus 1, but we're going to fix that problem. I'm still going to go ahead with u equals 3x minus 1. I'll get my du. I'm moving a 3 out of the way so I can see that my dx will eventually get replaced by a 1/3 du. Of course, I'll be able to replace the 3x minus 1 with u. But as for the extra x squared, well, what do we do with it? Revisit your u equation. I'm hovering over it right now. Solve it for x. This tells us that x itself is equal to u plus 1 over 3. So we can make this substitution in place of the extra x and then, of course, square it. Over on the right, you can see my work where I've made all three of the substitutions. Square root of 3x minus 1 becomes square root of u, or u to the 1/2. The dx is replaced with the du and the 1/3. Here's my value of x in terms of u squared, and now we're off and running. This thing still looks kind of nasty. We probably want to clean it up a bit before we do any calculus. So I'm going to very carefully square u plus 1 over 3. The 3 squared can come outside with the 1/3 that was already living there. So now I've got u squared plus 2u plus 1 multiplied by the u to the 1/2. And I'm still not done manipulating. I'm going to distribute the u to the 1/2 through here. And finally, at this third line of work, we have something that we can actually integrate. So I'm bringing down my 1 over 27. I'm applying my polynomial antiderivatives throughout. Be very careful with fractions. This first term, for example, is u to the 7/2 divided by 7/2. I don't like fractions in my fractions, so instead of dividing by 7/2, I'm multiplying by 2 over 7. You'll see that trick quite a bit today. Okay. The very last step of work, as usual, is to undo your original substitution, get rid of the u's. I get an answer that's pretty crazy looking. You do not need to simplify this or anything like that. You can leave it exactly as we have it here. Don't forget the plus c. Okay, so that's our first taste of this complete u substitution. The word complete is, as best I know, a reference to completely solving for x, and then therefore completely replacing all these x bits throughout the integrand using two different versions. Let's move that down to example 9. We're going to see more of the same here. Once again, stuff inside the radical is a pretty good choice for you. There is going to be this extra x in the numerator. That's okay, though. We can manipulate to see that x is replaceable with u plus 3. Meanwhile, du is just straight replacement with dx. Here is the updated integrand in terms of u. I had a root u on the bottom. I'm bringing that up to be u to the negative 1/2. Distributive property yet again. In this step here that I'm hovering over, we've got the actual calculus step, the antiderivatives, and then finally the replacement. Feel free to pause this video whenever necessary to make sure you are copying down work in your own handwriting or even trying the problems and then looking, okay? Let's move this over to number 10. Okay, starting to look a little more complicated. Um, in fact, we're going to do something a little bit different here. Um, what we're actually looking at is a version of a top 20. You might recognize from your top 20 list the integral that leads to an arc secant would have had, you know, an x in the denominator and then also a radical with something x squared minus a constant. This looks kind of familiar. So instead of using u equals 9x squared minus 1, we're going to go with u equals 3x. And that's because conveniently for us, the 9x squared happens to be some quantity all squared. This is the quantity 3x all squared. So my thought process is, let's try to replace the 3x with a u, and then that portion of my integrand will exactly look like a top 20, and that should carry us through to the end. Okay, so that's the thought process here. I'm relying heavily on my ability to recognize some patterns in here that look like a top 20. I go with u equals 3x. X then is u over 3. You can see my dx and du substitution as well. Moving back over to the right, we are swapping in those things that I've written to the left. X becomes u over 3. 3x quantity squared becomes u squared. Got an extra 1/3 hanging around from our du dx. All right. And actually, this 1/3 gets canceled because we have a u divided by 3. Dividing by u over 3 is the same as multiplying by 3 over u. So yeah, this 3 does land in a numerator positionally where you could cancel it with the 1/3. And upon doing so, what do you know? We land exactly where we wanted to. This now looks exactly like a top 20, just with u instead of x. So we know right where to go for the antiderivative. Don't forget the plus c. And then we end up undoing our substitution at the end. It's a little bit of a trickier one there. Trickier, I suppose. But that's how you would do it. Through the rest of these notes, in fact, we're going to see what we're getting into probably some of the most complicated problems for this whole chapter. In my opinion, the trickiest part of this chapter are the hardest U sub problems. You might disagree with that when you see some other things we do, but I personally think the hard U sub problems can be pretty hard. So make sure you're taking good notes. If there's something that doesn't make sense, you're asking me questions in class. You are going to see problems similar to these on worksheets. So I'm not just throwing them in here to make your life miserable. They are things that could show up. So with that being said, we're going to look at example 11. This one is presented as a differential equation. Find a solution means, well, it doesn't mean much in terms of our procedure. We're still integrating, but it does mean that our final answer has to be in the form y equals stuff. So just keep that in mind. All right. The reason this problem is showing up here is because it is possible to do it with a complete U sub. If you look back up to the right, I can show you how you would go about doing that. The big trick to remember if we wanted to do U sub here is it's generally always better to choose your denominator to be your u. If you don't believe me, you're welcome to try it the other way, but you'll probably get stuck, which could be a good learning experience to help convince you to set u equal to a denominator. And that's what we're doing in the case of this division of polynomials here. U equals 5x plus 4. Okay. You got your du, you got your dx equals 1/5 du. The complete u sub manipulation tells us that x is replaceable with 1/5 times u minus 4, which you could then slide back in on the top. I'm not going to go any further with it though, because it does get rather complicated even if you know how to start. And there is a quicker way to do this problem. So it's probably good to be aware of how you could use a U sub here, but I would prefer that you go with the easier way to do the problem, which involves polynomial long division. So just to be clear, the work we're seeing in blue down here is not related to the work in red. Those are two different approaches to the same problem. I'll leave it to you to follow the red work if you like. But here down at the bottom, we're going to use long division. Hopefully you remember how this works. I want to divide 2x plus 1 by the quantity 5x minus 4. So here's me setting that up long division style. Um, Sometimes people get a little intimidated by long division. It's probably not as bad as you remember. You've seen it before, you survived it. It's not going to be that bad. One of the key things to remember is you're only ever dividing one term with one other term at a time. You can see where I've highlighted 2x and 5x. That's all I'm doing to start. I'm going to take my highest degree term inside, divide it by the most powerful term outside. Of course, the result is 2/5, so I'm going to place that up above where I'm consolidating my quotient here. Once I've got the 2/5 down, I am going to multiply it by everything on the outside. You can think of it like a distributive calculation, 2/5 times 5x, write it down over here underneath. But then also 2/5 times -4, write it down underneath. And we're supposed to subtract that result from the like terms directly above. I like to put parentheses and a minus sign to remind myself of the subtraction. And if done correctly, that first column should just disappear. The second column is 1 minus minus becomes plus 8/5. I end up with a 13/5. Okay. Um, this remainder part here now has a lower degree than the highest term outside, and that's sort of a signal to stop. So what I'm going to do is just take this remainder and show that it still needs to get divided by 5x minus 4. Here's how I'm choosing to write that term. Okay. So long story short, this quotient is equivalent to what we started with. So I'm going to swap this in for the original fraction. And then we get on with the separation of variables. dy equals my quotient times dx. And now we're integrating. Integral of 2/5 is 2/5 x. Integral of this next thing here. It is actually technically a u sub on this 1 over 5x minus 4. I have skipped that work here, but the derivative of 5x minus 4 is just 5, which, it's going to lead to an extra 1/5 getting multiplied in when we do our swap outs. So I have skipped that work, but you'll see an extra 1/5. And then if I had had a u here, we'd be looking at the log antiderivative. So natural log absolute value of 5x minus 4 plus c. And then I'm just cleaning that up a little bit. This might seem kind of crazy, kind of a lot of work, but I still believe it's quicker than what would have happened to us if we went through with the U sub, where things can get a little bit nutty. So, you're welcome to try it if you like. All right. Think we're good for example 11. We're going to move on. I think I need to zoom out so it will let me move the page here. And we've got a few more examples. First of which is example 12. Yeah, this one's wild. I'm not gonna lie about that. I've labeled it as challenge. It actually looks like example 9, but just flipped, which, you might think it's the same pieces, just switched. How much harder could it be? It's a lot harder. So I've got a couple hints to help you out. I do think there's a problem like this on one of our worksheets. So we do have to be prepared for it. But my first hint is that problems like this tend to be easier if the radical is in the denominator. So to achieve that, you can see me multiplying top and bottom by root x minus 3, which actually works out really nice in our numerator. But yeah, now I've got a radical in the bottom. Okay. And I'm noticing that my numerator is two distinct terms separated with subtraction, which means we have the option of splitting this up into two integrals. And I do think that's going to make things a little better for us. So that's what I'm doing in the next step. Okay. At this point on, I'm going to color code these two integrals. The leftmost one I'm keeping over in blue. We get a nice cancellation of x's. I'm choosing to rewrite the radical in the exponential notation. But this first integral is actually really quick and easy. Again, you could do it as a u sub with u equals x minus 3. But I'm hoping by now you have noticed some patterns with these U subs, and you're maybe seeing a couple shortcuts. One of the things that might have come up already is that if our choice for U happens to have the same derivative as just a regular x, we don't really need to show U sub because our U value, in this case, I wrote x plus c, or really it's going to be x minus 3. Our U value is just going to behave like a regular x. There aren't going to be any extra numbers popping in as multiples when I go through the U sub. So I see something like this with a 1x minus 3, and I'm very happy because x minus 3 behaves the same as x plus any constant behaves the same as x. I can jump right down to my antiderivative where I'm using x minus 3, adding 1 to my power takes me to 1/2. And then I'm dividing by 1/2, which is the same as multiplying by 2. So I'm not really doing much work here. I'm spending way more time talking about it than time I would have spent doing it. This is just super quick to get here to here, thanks to the nature of what's inside this exponent, or rather, what's the base for this exponent. Okay, so that part's done. We're going to hold on to that, save it for the final answer. I'm jumping over now to the second integral, which is in red, and this is where things kind of go off the rails a little bit. I've got my second hint up here. Okay. We've been choosing the radicand, or the stuff inside a radical, to be our u pretty frequently. Here is the exception. If I have a radical in a denominator, and I also have an extra copy of x multiplied into that same denominator, this particular pattern needs us to do something weird. For the first time, I am going to include the radical itself as part of my definition of u. So in this case, u is going to equal square root of x minus 3, or as I've written it here, x minus 3 to the 1/2. Why does that work? Well, you will see very shortly, because when I take a derivative here, I get x minus 3 to a negative 1/2. I also have the 1/2 in front. But I can rewrite that as 1 over root x minus 3, which with a dx, which lines up really nicely with what we're seeing for a good portion of this integrand. dx over root x minus 3. Now I know what to do with it. I did have to move a 2 over, but I'm not so worried about that portion of it. Um, Meanwhile, the extra x floating around in there is going to require the complete u sub technique. We solve our u equation for x. I'm basically squaring both sides. Then I'm adding 3. But look how simple this turns out. Okay. Um, I have a 3 from the original numerator that I'm bringing down. I did move it to the outside. Okay. I have a minus sign from the original that I'm bringing down. Uh, my 1 over root x minus 3 dx from the original is all turned into a 2 times the du. I put the 2 outside. I put the du in its normal spot. And then the rest of the denominator is just a u squared plus 3. And after all that craziness, all of a sudden we've got a top 20 in front of us. 1 over variable squared plus a constant. That is an arctangent antiderivative. I do need to think about the square root of this 3. Usually we see a perfect square here. It doesn't have to be a perfect square. So I've got 1 over root 3 in front. I've got u over root 3 inside here. And then, of course, these constants and the plus c. And let's not forget that there was a whole other term from the first integral. So I'm now bringing all of that stuff down together. I'm undoing my u. And finally, we have an answer for this one. Okay, so in my opinion, this is about the hardest problem you'll ever see with a complete u sub. All right. There are still a couple other tricks I need to show you. I'm going to make my way up to the next problem. This is another weird trick that you might not ever think of on your own. I certainly didn't invent this trick. But luckily for us, this one at least is quick. So what do we do if we encounter an unfactorable quadratic in a denominator, typically 1 over an unfactorable quadratic? Is there a way out of this? Turns out there is. We're going to manipulate that denominator to get something that is factorable to pop up. And we're pretty close here. My thought process is kind of like, okay, x squared plus 4x, what would be the optimal constant to come after that? And the optimal constant would be one that completes the square. If you remember from algebra, the ideal constant over here, I would look at the constant on x, divide that in half, and then square it. So 4 lives here, cut in half is 2, square the 2 tells me 4. 4 is exactly the number I would want to follow the 4x to have a perfect square. Now, I can't just change a 5 to a 4 because I want it to be a 4. So as you can see, I instead replace the 5 with 4 plus 1. And I'm not going to worry about the 1 for a couple moments here. But what came before the 1 is now a perfect square, so we can slightly rewrite things. I now have 1 over quantity x plus 2 squared plus 1. And once again, we are in top 20 land. Even better, this x plus 2 is going to behave like a 1x, so I don't really need to show any u sub work. I can just treat x plus 2 as my variable. I'm going to go with arctangent x plus 2. It turned out it was ideal to have a plus 1 extra because that helped complete the top 20 that we're looking for, and we're done. All right. There are just a couple more examples, and there's nothing new here as far as integration techniques, but for the first time, I believe, we need to address definite integrals with u sub. How does that work? Well, we have to be quite careful because the bounds on an integral are bounds precisely for the specific variable that we're starting with. 0 and 2 are x bounds. If I'm going to switch to u as a different variable, I can't expect the bounds to still be 0 and 2. We have to convert the bounds. It's not hard, it's just a little bit of extra work, okay? In this problem here, we see the obvious candidate for u would be the x squared. Du becomes 2x dx. I like to get the x dx by itself because that's what I'm actually seeing in the original question. All right. But after that, I'm going to specifically look at my two original x bounds and just plug each one into this conversion equation. If x was 0, well, it turns out u would also be 0. So the lower bound, it doesn't seem to change. But if x is 2, u would be 4. So as soon as I update my integral to be in terms of u, I have to switch those bounds. This integral is only correct if I have a 0 and a 4 as the u bounds. If you leave the 0 and the 2, it's already incorrect. Even if you notice that mistake later in your work or try to switch back to x, your work is wrong if you don't have a 0 and 4. So in my opinion, the best strategy is to switch your bounds. And what's nice now is you don't ever have to go back to x. We can finish the problem in terms of u. This is a definite integral, so most likely we're going to get a numerical answer at the end without any variables at all. So there's no need to go back to x. Let's just use this problem as we see it. Fairly simple antiderivative. I'm just now plugging in a 4 and a 0 to this e to the u, and then clean it up a bit and we're done. Okay. Don't switch back to x. It actually makes more work. There's no need to do it. Last problem of the day, last problem of the video. It's another definite integral, this time with the complete u sub. Nothing crazy like some of the earlier problems today. We're going to stick with 3 minus x inside the radical as our u. Here's the solving for x, du, and then eventually dx work down below. But additionally, we're plugging in the original x bounds to this u equation. If x was 1, u would have to be 2. If x was 3, that would make u 0. Well, now these bounds are going to be in a different order than I prefer. Okay. So I have to be careful with that as well. I've swapped out the bounds in my work. I've brought over this extra negative that comes along with the du when I swap out my dx. I've got x minus 2 becomes 3 minus u minus 2, which in turn becomes 1 minus u. And then my radical becomes u to the 1/2. Now, I'm going to switch the bound order using our properties. And conveniently, when I do that, I lose the extra negative. I'm also distributing through here. And now we're ready to do the actual calculus step. I've got my antiderivatives. I've got my u bounds. I'm plugging in. It's nice to plug in 0 because everything disappears. So really all I'm seeing as my answer are the values I got when I plugged in 2. Okay. This problem is not considered super, super, super challenging. It's not the easiest one ever, but this is like a moderate, medium level, definite integral with a complete u sub that we should all feel pretty comfortable doing if we have to. Okay. I'm going to cut the video there. Thanks for watching. We should have some time for questions in class tomorrow, and feel free to email me as well.